Hi, welcome to week 5's recitation for CEE222. So let's get started with the problem 1, 4.5.3. So in this problem, we have the pipeline to deliver the oil, and we want to close the valve as soon as possible when we detect the leak, but not too fast. That will create a great pressure rise, which will damage the pipe. So the problem asks us to determine the minimum valve closure time that will prevent a large pressure rise. So how can we do that? Here's the information that provided in the problem. The pipe length is equal to 1,250 meters and the diameter is equal to 0.5 meter. The specific gravity for the oil is 0.85 and the bulk module is equal to 1.5 times 10 to the power of 9. And E stands for the thickness of the pipe, and Q is the flow rate, the flow rate under the normal condition. That's the oil delivery in this pipeline. And we want to solve the minimum valve closure time. Okay, so to start with this question, we need to first follow the definition. So the rapid valve closure are those in which the closure time is less than 2. Oh, that's less than 2L divided by the velocity of the pressure wave, C. Okay, and C, this speed of the pressure wave, C, is equal to EE divided by the, not E, sorry, this is EC, which is a composite module of electricity divided by rho to the square root. Okay, so a third equation that we will use is this EC. So EC 1 over EC will equal to 1 over EB plus dk divided by EPE. Okay, so if we can use this equation to solve for the EC, then we plug this EC to this equation, which we can solve the pressure, the speed of the pressure wave. Then we know the length of the pipe, which is equal to 1,250 meters. Then we can calculate the minimum valve closures time that we can have, which is this TC here. Okay, so now we have already understand the logic of how to solve this problem. Then we just need to plug in the value, then follow this step to solve backward, and we will get this easy. Okay, let's do that. Okay, so start with this equation. We know the bulk electricity of the water, which is equal to 1.5 times 10 to the power 9 Newton per square meter. Okay, it's here, right? And we know the diameter of the pipe, which is 0.5. This D is 0.5 meter. And what else would you know? This thickness of the pipe is equal to 2.5 cm. So we convert to the same unit, which is meter, that is 0.025 meter. Okay. And the EP, this is the module of elasticity of the pipe material, which is steel pipe, and you can get this value from table 4.1 on page 128. And in this table, they provide the EP value for the common materials of the pipeline. So you can just search from there, and you will get this EP equal to 1.9 times 10 to the power 11 Newton per square meter. Okay, so the only number that we don't know, we also need to solve for this coefficient K. And since the problem tells us this is expansion joint, and this coefficient is related to the joint type. So from the textbook, you can also find that if we have the expansion joint, then this K will equal to 1 minus 0.5 epsilon. Okay, and this epsilon simply is the thickness of the pipe. So this epsilon is equal to 0.025. So at the end, we will have this K value equal to 0.875. So we also know this K is equal to 0.875. Okay. So in this equation, we know all the numbers except this EC. So you can use your calculator and you will easily get that the EC, this EC, equal to 1.32 times 10 to the power of 9 Newton per square meter. Okay. And now, since we have the number for this EC, we just plug into the second equation, which this EC now is equal to 1.32 times 10 to the power of 9. And the density of the oil is the so let me write down here. The density of the oil is the specific gravity of time 0.85 times the density of the water. So the water's density is equal to 998 kilogram per cubic meter. Okay, so we will got the density for the oil equal to 0.85 times 998. Okay, so you plug this into this equation, then we can get that the speed of the pressure wave is equal to 1,250 meter per second. Okay. now we can move further up to this final equation I'm going to use. The C now is equal to 1,250 meter per second, and O is equal to 1,250, right? 150 meters. So we can get that this TC is 2 times this divided by this, and this just cancelled out. So T is equal to 2 seconds. And this is our final answer. So if the valve closes faster than 2 seconds, then it will produce a greatest pressure rise. So the ideal case is that the closure speed should less than 2 seconds. Should greater than 2 seconds. Sorry about that. Okay, so we have solved this problem. This is our final answer. 2 seconds. Okay, now let's look at the problem 4.5.5. Similarly, it's a pressure hammer question, but now the problem given the gate's closure time and want to determine the maximum pressure change in this question. So this question, we have a pipeline linked to reservoir to deliver water from the upstream reservoir to downstream reservoir, and the length is equal to 1,200 meters, diameter is equal to 0.5 meter, thickness of the pipe is 2 centimeter, the flow rate is 1.35 cubic meter per second, and the given closure time is 1.5 seconds. And because the problem also states that the water are freely moved horizontally in this pipe, that means the K factor is equal to 1. Also, even though the problem did not provide this EB, the bulk the elasticity for the water, you can find this number in textbooks, which I wrote here, is 1.6 times 10 to the power 11. Okay, so now let's try to solve this P. So from the textbook, we know that if this is the rapid valve closure, then the P, this delta P, can be calculated using this equation. Okay, so the first thing that we need to do is to determine whether 1.5 second is considered as the rapid closure in this system setup. So let's first do that. To do that, we already know the criteria that if TC is less than if TC is less than 2L divided by C, then it is a rapid closure. Okay, so we want to first calculate that. To do that, we need to calculate this speed of pressure wave. And we also know that the speed of pressure wave, C, is equal to EC divided by dou to the square root. And to calculate this EC, we will use this equation. That's 1 over EC is equal to 1 over EB plus D times factor K divided by EP times E. Okay, so that's fill in the value first. EB, as I given here, EB of the water is equal to 1.6 times 10 to the power 11, and diameter of the pipe is given here, right? So this is 0.5, and factor K is equal to 1 because it's freely moved set up. And the EP, similarly, you can find the EP value from the table 4.1. And here I just give you the value. That's EP is equal to 1.6 times 10 to the power 11. Okay, sorry, I wrote the number wrong here. The EB of the water is equal to 2.2 times 10 to the power 9. So I correct this number. This is 2.2 times 10 to the power 9. Okay, what else? E, the thickness of the pipe, is equal to 2 centimeter. 2 centimeter is equal to 0.02 meter. Okay, so we have everything that we need to use this equation. Then we can use the calculator to solve that. EC is equal to 1.64 times 10 to the power 9 Newton per square meter. Okay, now we can plug this EC to this equation as we did in previous question. This EC is equal to 1.64 times 10 to the power 9, and the density of water is equal to 998 kilogram per cubic meters. And then we can get that this C is equal to 1,280 meter per second. Okay, so we now have the speed of the pressure wave. Then we can further plug this value into this equation, which L is equal to 1,200 meters. So 1,200 meters, and C is equal to 1,280 meter per second. And let me write down here. The TC is equal to, if you calculate this, 2 times 1,200 is equal to 2,400, and you divide that number to by 1,280, and you will got that TC is 1.88 second. Okay, but the problem gave us is that we close the valve within 1.5 seconds, so it's less than this critical value. So we consider, let me change the color. We consider the current setup, current system setup as the rapid closure. Okay, so we verify that. Then to calculate the change in pressure, we can now use this equation. And to that, we already know that the density of the water equal to 998 kg per cubic meters, and we know that C, the pressure of the wave, the speed of the pressure wave, that's equal to 1,280, and the velocity let me write down here, the velocity is equal to the flow rate divided by the area. Okay, and you know the diameter is a circular pipe, so you just calculate the area using this equation, and you know that this d is equal to 0.5. So you plug this value a into this equation here, and we also know that the flow rate that in this pipe is equal to 1.35, sorry, 1.35. So you will know the velocity is equal to 6.88 meter per second. And now you can plug this velocity into this top equation. So the velocity now is equal to 6.88 meter per second. And then you just times these three numbers up, then we can get that the delta P is equal to 8.79 times 10 to the power of 6 Newton per square meter, which is equal to 8.79 megapar. Okay, then we solve this problem. So let's do a really quick review. This is the information that gave by the problem. And because we want to calculate the pressure change, which is this equation, if the system setup is considered as the rapid closure type. So in order to verify whether this is a rapid closure, this 1.5 seconds is a rapid closure time, we need to calculate this equation to find out this criteria that determine the rapid closure or the normal closure. To do that, we need to calculate the speed of the pressure wave, and here is the equation that you should use to calculate this C number. To do that, we need to calculate this EC, and the EC can be calculated using this equation here. And just plug in the number, you calculate the EC, you plug back to this equation, and you calculate the speed of the pressure wave. Then you put that C back to this equation, and then you can find out the criteria for the closure time is equal to 1.88 seconds here. And you found that 1.5 seconds is less than 1.88 seconds, so we consider this system setup as the rapid closure. Then we can apply these equations to solve the pressure change. And to apply this equation is really simple, because you already know the density of the water, you know the speed of the pressure wave, and now you can calculate the velocity inside this pipeline using the flow rate information, because we know that the flow rate is equal to the velocity times the area. So you just inverse that equation, and you can see that the velocity is equal to the flow rate divided by the area. And area can be calculated using this equation, because it's a circular pipe, and you know the diameter, so you can plug in the number and you calculate the area, and you plug in back to this equation, and you get the velocity. And you get the velocity, you further plugging back to this initial equation that we want to use to calculate the change of the pressure. And now you can get the final answer that equal to 8.78 megapar. Okay. Okay, now let's look at the problem 4.5.8. This one is really similar to the previous problem, but instead of solving the pressure change, Now we want to solve the thickness of the pipe to withstand the pressure change equal to 250 psi. So we can have the initial case, not initial case, but we will solve this problem with the opposite direction with that three equation that we used in the previous equation, in the previous problem. So now let's do that. To start, we know that if in a rapid closure problem, the pressure change delta P is equal to low CV0. Okay, and we already know that this problem is a rapid closure problem, so we can apply this equation to solve C. Because we already know that the density is equal to 1.94 slug per cubic feet. Okay, and we can calculate the velocity using the equation that we should already be familiar with. That's the let me write here. V, the velocity V0 is equal to flow rate divided by the area, and the flow rate is equal to 1.45. CFS divided by the area, which is 2 over diameter, diameter over 2 to the power of 2 times pi. And the D, because it is cubic feet per second, so we need to use the unit equal to feet. And this is the unit conversion from inch to feet. So we just plug this 8 over 12 into this equation, and you can calculate the velocity. Which the velocity is equal to 4.15 cubic feet. No. Feet per second. Okay. So we now further plug the velocity back to this equation, and we know the pressure change is 250, and we need to do the unit conversion from inch to feet, and because this has a square, so we need to times 12 square. Okay, so let me just rewrite this equation down here so we can have a better view. And now let me change it back to green color. So 250 times square of 12 is 144, equal to 1.94 times C times the velocity. And from this equation, we can solve that the speed of the pressure wave equal to 4,470 feet per second. Okay, And then we can plug into our second equation, which we know that the C is also equal to the square root of EC divided by the density. Okay, so again, we know the density is equal to 1.94 slug per cubic feet, as we show here. Also, I write down the information here. Then we can solve this equation, which will get that EC is equal to 3.88 times 10 to the power of 7 pound per square feet. And do the unit conversion, we will get that this is also equal to 2.69 times 10 to the power 5 pound per square inch. Okay. And we can further apply this EC to the third equation, which is related to this thickness. So let me write down the equation. That's 1 over EC is equal to 1 over EB plus dk divided by EP times the thickness of the pipe, which is the value that we try to solve. Okay, so let's start to plug in the number. We know the EC equal to 2.69 times 10 to the power 5, and we know the EB of the water, which is equal to 3.2 times 10 to the power of 5 pound per square inch. Okay, I think you can find this value in the textbook or Google it if you're able to get this EB value for the water. And the diameter of the pipe is equal to 8 inch. And EP is equal to 2.3 times 10 to the power of 7 Newton per square meter. You can find this EP value from the table that we keep mentioning. And this is iron pipe, so you just find the corresponding value for the iron pipe. And we also need this K value. And because the problem already tells that this is two anchored pipeline, so we will use this equation to calculate the K value. And this epsilon is the Poisson's ratio that we normally will use 0.25 for most of the cases. So we just plug this number into these equations, we will get the K equal to 0.938. Okay, so this K is equal to 0.938. Okay, so now in this equation we know every variables. The only variable that we don't know is this thickness of the pipeline, which is the parameter I will try to solve. So use your calculator and you can solve this E. that E will equal to 0.626 inch. Okay. Okay, now let's look at the problem 4.6.3. So to the pressure hammer problem, the alternative of the closure speed to prevent the pressure rise, we can also use this surge tank, which the water will rise in this tank to compensate the pressure that creates by the rapid closure. So the question asks us, given the information that I show here in the blue color marker, what is the area of this surge tank that should have in order to satisfy the criteria? Okay, so let's first look at the information I gave by the question. The maximum of the water level rise is equal to 16.5 feet, and the length of the pipeline is equal to 3,450 feet. Diameter is equal to 6.5 feet. The flow rate is equal to 460 cubic feet per second. And this number that I write in the pink color is information that you can find in the textbook by looking for the material of this pipeline. Okay, so let's start to solve this problem. The problem tells us that we can ignore the minor losses. We only need to consider the head loss for the friction due to the friction in the pipeline. And we need that information in order to solve this problem. So let's start with that. If you still remember, the head loss due to the friction is equal to this equation. Head loss of the which contributed by the friction head loss is equal to the factor F times L divided by diameter times the velocity term. Okay. And we need to find out this factor F. And if you still remember, the factor F can be found by the Moody diagram using this information here. So we need to first calculate these two information. Let me change the color. The E I already gave you is equal to this. So this E divided by D is equal to 0.0006 divided by D diameter 6.5 feet is also feet. So we know that this is equal to 0.000092. Okay. And the Reynolds number, as I show here, the Reynolds number is equal to the velocity times the diameter divided by the dynamic viscosity of the water. So the velocity, how do we calculate the velocity? We have the flow rate here. This will equal to the area times the velocity, right? And the area is not the area is it's not the area of the surge tank. It's the area of this, the cross section of this pipeline. So we know the diameter. The area will be 2 over D to the power of 2 times pi, and you can do the calculation. That we will get V is equal to 13.9 feet. Let me write it down here. So that's velocity equal to 13.9 feet per second. So we know the V, we know the D, we know the viscosity value. So let's just plug in the number. 13.9 times the diameter 6.5 divided by the viscosity 1.08 times 10 to the power minus 5. Then we get the Reynolds number equal to 8.37 times 10 to the power of 6. Then you use these two information and the Moody diagram, you should be able to find that F is closer to 0.012. Okay, so now we can further plug this F into this equation. That's this F is equal to 0.012, L is equal to 3,450 feet, diameter is equal to 6.5 feet. The velocity term, that's V is equal to 13.9 feet per second, and the G for the English unit is 32.2. Okay, so we have all the number that we need. That this will equal to 19.1 feet. Okay, so we got the head loads that we need for the further calculations. The next step is that we need to determine the damping factor. Okay, so to do that, let's first calculate the pipeline friction factor, Kf. Kf is F, the factor F times L divided by 2G diameter. So basically, this Kf is equal to the head loads divided by, the friction head loads divided by the velocity square. So basically take this velocity out, and then you get this coefficient as HF, we just calculate that is equal to 19.1, and the velocity we also have that's equal to 13.9. So you can easily get this KF, the friction factor for the pipeline, that's equal to 0.0989 second squared feet. Okay, so next we can then calculate the damping factor using the equation show here. That should I oh no, okay, that's fine. Y mix plus the water head loads divided by the damping factor beta equal to the log scale of the damping factor divided by beta minus Y mix. Okay, and we know the Y mix is equal to this value, So this is 16.5. This is 16.5. And halos we have just calculated is equal to 19.1. So again, use your calculator. We can solve that the beta is equal to 19.9 feet. Okay. And I need to clean a new section to write the rest of the stuff. Let me erase the top part. Okay. Oh. Okay, let's continue. So we now know the beta, which is a damping factor equal to 19.9, and we also know that the damping factor equal to this number. Okay, and these equations include the information that we want to calculate, which is this AAs, the area for the surge tank. So now let's fill in a number. The length of the pipeline is equal to 3,450. The area is equal to 2 over d square pi. The d is equal to 6.5 feet. And g for the English units is 32.2. The Ka that we just calculated here is equal to this value, 0.0989, and the beta, we already know this. This is equal to 19.9. Okay. So the only number that we don't know in this equation is oh, sorry, I made a mistake here. As I said, this area is not the area of the pipe. Oh yeah. That's, let me write. This is correct. Sorry. The diameter is equal to 6.5. Okay. Sorry. The only thing that we don't know in this equation is this area of the surge tank. So similarly, use your calculator, then we can get this AAs equal to 904 square feet. And if you translate into diameter, then the diameter of this ace will be 33.9 feet. Okay, so we found that the diameter for this surge tank is actually quite large. And so the engineer might want to redesign this entire project because this diameter might not be that cost effective in a sense. Okay, so this is how we solve it. Let's just do a quick review. What did we do for this problem? Because we want to solve the area of this surge tank and over the equation that you have learned, the equation that is related to this AS is this damping factor. Okay, so to solve the damping factor, we can use the equation down here. And because in this equation, we also need to know the halos. So the problem tells us the halos, we only consider the friction halos and ignore other minor halos. So we just use the friction halos equation to calculate these halos. And follow what we have learned in previous recitation. We know that we can use the Moody diagram to find out the factor F, which will help us to calculate these friction halos. And you just plug those numbers in and you solve this beta, which is a damping factor, and use the other equation for the damping factor, you can solve the area for the surge tank. Okay. Okay, now let's look at the problem 5.1.3. The question is that we have the earth line shown here, and we have a pump to suck the water up and drain to the downstreams to prevent the overtopping issue if the water level is too high in the reservoir. And the pump, the total energy that we need to pump the water from this reservoir over this dam is equal to 2.43 meter. Okay, this is meter. And this is the really old pump. So the efficiency is only like 50%. And the total power can provide by this pump is equal to 1000 watts. And the other information that we will use is the surface area of this pump. Surface area of this reservoir, the lake. And the question asks us, what is the drawdown that if we use this pump to suck the water out for 2 hours? Okay, this is the question that we try to solve. And the question, the problem also tells us the change, this h, will be small. So so instead of using the integration that we use in the first recitation, here we can use a more simple method, which is kind of an approach to approximation to this problem, because the change is small, so we don't really need to use the integration to calculate that. Okay, so let's start to solve this problem. First, we want to know how much power that the pump really used to suck the water up. So to do that, we know that the power provided by the pump, the actual power really applied to the water is 1000 watts times the efficiency, which is 50%. So that gives us the energy that used on the water is equal to 500 watts. and we can also, the watt is equal to the Newton times meter divided by second. Okay, and we know that the power equal to dou Q HP. Dou of the water is equal to 9,790 Newton per cubic meter times the flow rate, and this is the variable that we try to solve, because if we know the flow rate, we can estimate the total volume that we can draw using this pump for 2 hours. Okay, and times the energy that can provide by the pump with the total energy that we need to suck the water up, which is provided by the problem, is equal to 2.43. So this is 2.43. Okay, this is 2.43, and the power is of the pump is 500. Okay, so from this equation, we can solve that the flow rate is equal to 0.021 cubic meter per second. Okay, and to calculate this H, the drawdown, we note the volume is equal to the area times the drawdown H. So in other words, we can calculate this H using volume divided by area. So how can we calculate the volume? Volume is equal to the flow rate times time. So the flow rate, let me just plug in a number directly. The flow rate we already solved is here, 0.021, and the time, the question tells us we want to draw the water for 2 hours. So it's 2 hours, and we need to convert it to the second. So 2 hours times 60 minutes times 60 seconds. Okay, so we can solve this volume yeah, that's policy here. So we can plug this volume into here, and we know that the area is equal to 5,000. So this is 5,000. So the entire the drawdown H is equal to 0.021 times this is 7,200. Okay, so this 7,200 divided by 5,000, and this will give us that the drawdown is equal to 0.0302 meter, which is equal to 3.02 centimeter. Okay, so we have solved this problem. Okay, here comes the final question for this week's recitation. The problem 5.1.5. So in this problem, there's a pump in this pipeline to deliver the water from reservoir A to reservoir B, where the elevation differences is equal to 20 meters. So the problem asks us, given the information that I show here, what is the power of the pump that we need in order to deliver the water from reservoir A to reservoir B? And the flow rate requirements is equal to 2.05 cubic meters per second. And the question also tells us the pump efficiency is equal to 80% and the motor efficiency is equal to 74%. And the length of the pipeline is equal to 100 meters and the diameter of the pipeline is equal to 80 centimeters. Okay, so how do we solve this problem? It's actually pretty simple. First, we need to write down the energy balance equations. So I guess you already know that the energy balance equation is the height of this reservoir A plus the energy that provided by this pump will equal to the height of this reservoir B plus the corresponding halos. Okay, so we will use this equation. And we already know that the B minus A, the HB minus HA is equal to 20 centimeters. So the energy that we require from the pump will equal to HB minus HA plus the halos. And we know that the HB minus HA is equal to 20. So the problem is we need to solve these halos. Okay, so let's jump into the next section to calculate that halos first. So I hope you still remember the halos equation that is equal to the friction halos plus the minor halos, which is the summation of the coefficient K times the velocity term. Okay, and the minor halos that we consider in this problem is the entrance, is KE, and the axis KD. Okay, and the KE is equal to 0.5 and the KD is equal to 1. Okay, that's the number that we're going to use for our minor losses. And so let me just write the number down here, okay? So 0.5 plus 1 is 1.5. That is this term will be. So how do we calculate the friction halos? The friction halos is equal to the factor times these terms. Okay, and to determine F, we need to use the Moody diagram with these two numbers. And I already tell you that the E is equal to 0.6 millimeter because the pipeline that we use here is the rough concrete. And you can find this value in the textbook. So that is probably in the number 0.6 millimeter. And the diameter is equal to 80 centimeters, which is 800 millimeter. And the Reynolds number is equal to velocity times the diameter divided by the viscosity. And if you just plug the value here, we will know that the velocity, we don't know the velocity yet, right? But because we know the flow rate, so the flow rate will equal to A times V, and we also know the diameter, so we can calculate this V. So here, to save the time, I just give you the number for the velocity, which is equal to 4.08 meter per second. Okay, so if we have the velocity here, we can just plug in the equation that I show here. So the velocity is equal to 4.08 times the diameter is equal to 80 centimeter, which is 0.8 meter. And the dynamic viscosity of the water is 1 times 10 to the power of minus 6. Then we can guess this number is 3.26 times 10 to the power of 6. And you use this information and the random number to search on the Moody diagram, and you can find out the factor F is 0.0185. Okay, so we can further calculate the friction head loss, because now you know this number is 0.0185, and the length is 100 meter, 100, and diameter is 0.8 meter. Velocity is 4.08 meter per second. G is equal to 9.81. So you know every value. Then you can plug these friction head loss into here. And similarly, this G is equal to 9.81. The velocity is 4.08. And you know that summation of the K is equal to 1.5. So you know everything for this equation. And we can calculate the head loss. Total head loss is equal to let me see. Actually, I didn't calculate that individually. So okay, assuming that you have calculated this, because I didn't calculate this number out for you. So assuming that we have these head loss by using calculator and plug all those number in, and you should be able to get this head loss, and you plug this head loss back to here. So here is the head loss that you have. Then we can calculate the energy that we need from the pipe, from the pump, and that gives us HP equal to 23.2 meter. Okay. So let me set it again. This is how you calculate the water head loss. And for the friction head loss part, you use the Moody diagram to find out this factor F and plug in this equation. Then you can solve the value for this HF. And you know the minor head loss, we consider the entrance and the excess. So to sum these two K up is equal to 1.5, and you know the velocity from the flow rate, then you can calculate the total head loss from this equation. And you plug back here, and then you simply 20 plus this head loss will equal to 23.2. So that means the head loss that we calculate here should equal to 3.2 meter. Okay. Now we have the total energy that we need from the pump. But the question asks us is the power that required for this pump to work properly. So we need, the first step is to translate this energy to the power. How can you do that? Let me write up here. The power will equal to dou Q H P. And the dou is the density, so it's 9.79. Okay, then times the flow rate is 2.05 times the energy required for the pump, 23.2 from here. Then we know this is equal to 466 kilowatts. Okay, is this the end of the calculation? No, it's not, because this number only true when we don't have any, when the efficiency equal to 100%. But from the program, we know that neither the efficiency of the pipe or the motor equal to 100%. So we need to take this into account. So the final, let me change this notation. I should write the PM, the power for the motor. So the PM should equal to this requirement power divided by those two efficiency, 0.8 and 0.74. And we will get the final power that we need to provide to this pump, which is equal to 787 kilowatts. And that is our final answer for this problem.